having deja vu and amnesia all at the same time. Okay, it's over. Hello, welcome to the beginning of a new unit in pre-calculus. This time it's unit 6, and we're still looking at quadratic stuff. This time it's analyzing quadratic functions instead of solving quadratic equations. There's definitely a lot of overlap there, which is good. So there's a lot of things that we've kind of learned already, a few more things that we haven't learned already. So let's get into it. You should have your unit 6 note packet, and that looks like it's, well, kind of focused. Okay, that looks even better. And so here we go, the unit 6 notes, analysis of quadratic and square root functions. As we turn the page here, it's going to give us 6 quadratic functions for us to kind of analyze a little bit. The first thing it asks us to do is to write down the domain of each of these functions. And I'm just going to clue you in here that the domain of every single quadratic function is all real numbers. And so in each of these domain spots, we can put in negative infinity to infinity because that's the domain of every quadratic function. In other words, quadratic functions are defined for all real numbers as their x values. Okay, for the range of each of these, now if you know the vertex and you know whether the graph opens up or opens down, then you can tell the range. In this case, the vertex has a y-coordinate of 4 and the rest of the graph exists below that. So the range is all numbers less than or equal to 4. Notice the bracket on the 4. This one right here, the negative 4 is the lowest y value of any point. So our range is negative 4 to infinity. Same on the next one. The next one, the vertex has a y-coordinate of 3, and that is the largest y-coordinate of any point on that graph. So the range is negative infinity to 3 inclusive. The next one is negative 4 to infinity. And the last one is all numbers less than or equal to 5. As for the axis of symmetry, the axis of symmetry is this imaginary line that goes right down the middle of our parabola, and every single parabola has this symmetry. Every single parabola is symmetric over that axis of symmetry. Okay, and here's this one as well. And finally, this guy. Notice that that axis of symmetry goes through the vertex of the graph. Since our axis of symmetry is a vertical line, meaning that every point on that line has the same x coordinate, then when we write its equation, the equation is x equals some number. That number is whatever the x coordinate of all of these points is. In this case, all of these points have an x coordinate of -1, so the axis of symmetry is x equals -1. This axis of symmetry would be x equals 2. The next one is x equals -1 again. Bottom left, the axis of symmetry is x equals -2. The next one is x equals 1. And finally, x equals -2 again. Okay, so that's how we find the axis of symmetry. On the next page is this big table that they want us to fill out, and we're actually not going to do that. You can if you want to. The notes that I posted in Schoology have all of this filled out already. I'm going to go ahead and display the one where everything is filled out. I don't expect you to fill them out right now. I just want you to kind of pay attention. First of all, it says, what is the value of a? Keep in mind that all of these functions are written in the form y equals ax squared plus bx plus c. So these are the numbers it's referring to when it talks about A, B, and C. Now what I did here to fill out this table was each of these functions gave me the equation for it, and so I could see the value of A, B, and C. Okay, you'll notice here that when the A value is negative, the graph is concave down, meaning it opens down. So this graph opens down like that. When A is positive, the graph is concave up, and so it opens that way. So the sign of A determines whether the graph is concave up or concave down. If the graph is concave down, then the end behavior would be that on both sides of the function, the y-coordinates go to negative infinity. So I would read this as the limit of f of x as x approaches positive or negative infinity is negative infinity. What that means is as x gets infinitely large, meaning we go to the right, and as x gets infinitely small, meaning we go to the left, the y values on both ends go down and they get infinitely small. So they go to negative infinity. Whereas if the graph opens up, then the limit of the function as x approaches positive or negative infinity is positive infinity because the y values are going to infinity. So you see when it's up, the limit is infinity. When it's down, the limit is negative infinity. It asks us to do this negative b over 2a thing. It says, what is the value of x equals negative b over 2a? And you may be asking, where does negative b over 2a come from? Good question. That's a question I answered in class. We're not really going to go into it in the videos. It comes from the quadratic formula, but I went ahead and found the negative b over 2a, just using my b value and my a value, and then it says find the value of the function using that x coordinate. So after finding negative b over 2a, I pretended that this was my x coordinate. I plugged that number in for x into each of the functions and found the y coordinate, and then I looked on the graph at what the coordinates of the vertex were, and you'll notice here that there's definitely a relationship here. So the negative b over 2a is going to find for us the x coordinate of our vertex. By plugging that x coordinate into our function, we find the y coordinate of our vertex. It asks if the vertex is a maximum or minimum. Well, this depends on whether the graph is concave up or concave down. If the graph is concave down, the vertex is the highest point on the graph, and therefore the vertex is a maximum. If the graph is concave up, then the vertex is the lowest point on the graph, and therefore the vertex is a minimum. As for the value of c, that's the constant term, and we already know that c is going to tell you the coordinates of the y-intercept. So I went through each of those functions and looked at the c value, and then I knew what the coordinates of the y-intercept would be. If the constant term is -3, the y-intercept is 0, -3. The constant term is -1, the y-intercept is 0, -1, and so on. Okay. For this next page, I'm going to go ahead and stick with this that's already filled out. Everything that's listed here is what I just explained. Whether A is positive or negative, that tells you whether the graph is concave up or concave down. It also tells you whether the vertex is a maximum or a minimum, and it determines the end behavior. Negative b over 2a tells us the x coordinate of the vertex. If you plug that number into the function, that gives you the y coordinate of the vertex. 0, c is the y-intercept, and there's one other thing here, which is that axis of symmetry is always directly in the middle of the two x-intercepts. You can see that on each of these graphs. The two x-intercepts are evenly spaced on either side of that axis of symmetry, and that's true in each of these graphs. Okay, for the next example, I've gone through and factored each of these functions. If you need to pause and get the factored form, you can. We've already learned this as well, that once you know the factored form, you can find the zeros. So if this factored form is x minus 4 times x plus 2, the 0 of x minus 4 is positive 4. The 0 of x plus 2 is negative 2. My zeros are 4 and negative 2. That also tells me that my x-intercepts are 4, 0, and negative 2, 0. So the zeros of the function also tell me the x-intercepts of the function. The only exception to this is if the zeros are non-real numbers. In that case, your graph just doesn't have any x-intercepts. So the zeros are the x-intercepts unless the zeros are non-real numbers, in which case your graph just doesn't have any x-intercepts. On the next page, we're going to do this process backwards. where we're going to be given the zeros and we're going to be asked to find the factors and ultimately the equation for the function in standard form. Remember, roots and zeros are the same thing. One of my roots is x equals -4. Think about what that factor would be. What factor can I set equal to 0 and get x equals -4? Well, that factor would be x plus 4. If you set x plus 4 equal to 0 and solve it, you'll get x equals -4. How about if my root is x equals 1/4? What would that factor need to be? Well, that would need to be 4x minus 1. If you set 4x minus 1 equal to 0 and you solve that, you get x equals 1/4. So if x equals 1/4 is our root, then 4x minus 1 is our factor. If I multiply these factors out, if I just FOIL this, I get 4x squared. Let's see, 16 minus 1 is 15x minus 4. There's my function in standard form. And I just FOILed those two factors. Let's do this one more. If your root is x equals -2/5, if you need some help with this, just think of it this way. Take x equals -2/5, multiply both sides by 5. 5x equals -2. Add 2 to both sides. See, and now I've got 0 on one side. That 5x plus 2 is my factor. Because if you set 5x plus 2 equal to 0, you get x equals -2/5. If your root is 2/3, then your factor is going to have to be 3x minus 2. That's the thing that if you set it equal to 0, you'll get x equals 2/3. I want no factors in my factored form here. Now, if I multiply this out, 5x times 3x is 15x squared. My outer is -10x. My inner is 6x. That adds up to -4x. 2 times -2 is -4. There we go. Okay, that is section 6.1. We did it. Hooray. Okay, go on about your day. Talk